that much of what you call primer, you can just start up with the overall exercise. Thank you. Thanks, Abha. So let's wait for to maybe 120 or maybe 3-4 minutes, and you can explain how to. So see, so the aim is you should be able to given a different process scenario, you should be able to develop an analogous model. This doesn't have to be what you call the tanks, or it could be anything. You see that? So the idea, what you need, the take home message is that how given the process specification, what all things you need to do. So that should be the take home message. Okay. So Abar, I think you can help them. Am I audible?
Yes, sir. Yes, sir. So we just have to do the mass balance to find the equations for the H1 and H2 first of all. So what we can do is we can write it as the accumulation of A1, which will be equal to what?
So Abar, I think you are not sharing the solutions. Please share that.
Okay.
Then you can explain one by one.
So is my screen visible?
I think the tutorial question is only visible.
Okay.
You can switch between the tutorial and this, showing the problem sketch and the steps that you need to take.
Okay. So first two equations would be we can use the conservation of mass here for the just wait. Okay. So we can use here the what is the accumulation of the A1 in here. So that would be equal to rho A1 dH by dt, and that would be equal to the inlet we are getting minus the outlet that is getting out. So the first equation for the H1 and with respect to time, the dynamic model would be this. Similarly for H2, we can see here that there is no inlet stream, only the W2 is here. So dH2 by dt would be equal to the W2 with respect to time. For W2 and W3, we can use the resistances from here and we can model the equation as W2 would be equals to P1 minus P2. P1 is the pressure for on this the H1 height cylinder, and P2 is on the H2 side cylinder. So the P1 minus P2 that would be divided by R3. So that would be our W2, which is the flow, and we can write it as this. H1 and H2 are the terms. We can write it as in terms for time. Similarly for W3. So we can get these four equations through conservation of mass. Now, if we can see our, our question, we can say that there are seven parameters in this question. First is the seven parameters which are constant. First is the rho, which is the density of this liquid. Second is A1 and A2, which are the areas for these bottoms. Third is the gravitational constant, which is G. And the next are R2 and R3. In these constants, apart from these constants, we have five variables which are changing. First is the height, the H1 and H2, and the flows, the flow rates, W1, W2, W3. So we have five variables and four equations which we have get from here. So the freedom, what's it, the freedom. So we have these. So the freedom degrees of freedom would be five minus four. So we are getting one. So if we are getting one, then we have to assign a variable into input or output or something else so that we can carry out, so that we can get an exact solution. So the W1 here is a function of time, which we have already done there. So we can write W1 as input and we will have four outputs if we have four variables. Then we can specify that we will have exact solution if we assign W1 as our input. Do you have any doubt in this?
So any questions so far? Yeah, you can keep the solution there, and if you
You
have any
can,
questions, let's discuss that.
using the conservation of mass, you can derive these four equations, which is very simple. And we know that there are five variables which are changing, seven parameters which are constant. So the degree of freedom would be one. We have to assign a variable so that we can get an exact solution. We know that the input variable is W1 and it is a specific function of time. So we get four outputs and our equation is available. Any doubt regarding this question? Okay, then to move on to the second question.
So just wait. Maybe we'll ask once more. Any clarification needed? So make sure that you understand this well. So any issues? Anyone in the participants, starting from Achutosh to Prakash? Any issues that is not clear? So shall we assume that you understood this? You can at least speak up that so that we'll move on to the next question.
Yes, sir.
Okay, then Abar, you are good to go.
Okay, so you can try the second question. In the question is similar to the first question, but here we have only one cylinder, and in this question there is a gas, PG pressure up here, and we have to find whether the equation we derive or the operation of the system is dependent on the ambient pressure PE. And we have to also determine if this is dependent on PA if we are dealing with an open system. So start with the mass conservation and use an equation which has been I think taught you in the class, which is Q equals to CV into root of P minus P by rho. Equation for Q.
So I'll just add. See, so it is all about flow modeling. Okay. The Wall coefficient is generally okay. So you would either what I would say use the Wall coefficient in the modeling, or you use the resistance in the modeling. Generally, Wall coefficient would be inverse of the resistance. So in the previous case, we have used resistance as an inverse variable, or if you I don't know if you do, when you have done your fluid dynamic experiment, they tend to use the variable Wall coefficient. So the aim of this particular question is to kind of help you to understand those different terminologies. So you might encounter the flow as a rate of change of driving force divided by resistance, okay, or Wall coefficient times the what you call the driving force. Wall coefficient technically would be most likely would be inverse of the resistance. So that's what here this question says. So here so the valve is given and valve coefficient is given. So you will have to understand that is 1 by resistance. So that's absolutely fine, but you only need to use them as it is. But again, one difference here is saying that uh, so what is the driving force? So the driving force there was not that in the previous question was little bit more easier, basically just the flow rate difference. But here you see it is a closed container. So there is some gas on the top, okay? So that kind of insert pressure, okay? So, and there is also the liquid that would insert the pressure, and the jet is ejected to atmosphere. So that is the total driving what you call the force balance you have to build around these three variables: the pressure exerted by the gas, pressure exerted by the liquid column against the atmospheric pressure. So this is the overall understanding that you need to take care while solving this. Okay, Apar, thanks. So let them, we'll give them maybe 5-6 minutes and let them try to solve. And also, it is written, it is not a linear driving force. I think somewhere it has written in square root, right? A square root relation. So, in contrast with the previous example where you assume that flow rate is a linear relation between the rate of change of driving force, here it is a square root relation, which means that a square root would prevail on the driving force. So keeping these things in mind, you can try to attack the problem. Thank you. Yeah, maybe Par, you can explain them, help them with the steps.
Okay, so in this equation, in this problem, we will start with the basic mass conservation problem, the mass balance. So we will uh, take the accumulated mass in this closed cylinder, which will be equal to the difference between the inlet and the outlet. So it would be equal to the mass accumulated due to the water or the fluid plus mass accumulated to the gas. That would
So
be
your
equal to
voice was not
the,
clear.
sorry,
So your voice is not clear.
just wait. Am I audible now?
Yes, sir.
Okay, so what I was saying is we will first apply the mass balance on the cylinder, which would be equal to the mass accumulated due to the gas plus mass accumulated due to the liquid, and that would be equal to the difference between the inlet and the outlet flow rate, right? So the mass accumulated due to the liquid plus mass accumulated due to the gas, which would be equal to rho Qi minus Q, which is the mass flow rate. But because mass accumulated due to gas and our area is constant, we can simplify this equation to this A dH by dt, which will be equal to Qi minus Q. Now, using this square root relationship, which is equal to CV, pressure outward minus pressure inside, and using the ideal gas law, we can convert this equation into this. Now, if you see closely, when we have a closed tank, then Pg would not be equals to Pa, and our model equation would dependent on Pa, which is the atmospheric pressure. But when we have an open system, then Pg would be equal to Pa, and these two terms would cancel out, and our system would not be dependent on Pa, which is the atmospheric pressure. So that is what we are trying to find in this question. So do you have any doubt regarding this question or the solution which I saw? Any clarification for?
No, sir.
So let's move on to the next question if there is no clarification. So in this third question, you can try the third question. In this, we have a dynamic model equation which we are given, and we have to find the Laplace transform. We do not have to find the exact Laplace transform of this equation. We just have to find the time functions which will appear in the YT if we are using the UT as these two equations. We do not have to find the whole equation. It's a bit tedious. So just find the time equations and what will be the values of the variable. Use the input functions which we are given.
So thanks, Apar. So this question is like a recap what you have learned in your MTL courses, application of Laplace transform to convert ODE into corresponding algebraic equation. So you can use those principles. So you are given with an ODE. This is so even if you look at your previous question, when you derive the expression, finally it resulted in an ODE in the first two questions. So if you are given with an ODE per se, and as we have mentioned in the class, it would be much more easier for us to work in the Laplace domain because the what you call the ODEs become algebraic equations only in the transformed space. So the idea here is okay, if you are given with an ODE, can you convert them into the Laplace? Okay, recapping your previous Laplace transform what you call experience, and what all things to be done. So you can just think of and figure out what to do, and we will maybe wait till 1:45 or so, and at least start with. So try to solve the first problem maybe. So it is given there are two forcing functions, which is b is equal to 2 power e raised to minus t, and second is ut is equal to ct. At least try to solve one of that and try to see what are you getting in. So think about your recall your Laplace transform experiences, and if needed, you can use the table. Of course, everything. So far, you can kind of help them.
Yes, sir. So let's start with the first option, first part of the question, which is ut equals to b e to power minus 2t, and we just apply the whole the Laplace transform on both sides of the equation, and using the standard Laplace properties, we will get the equation. We get this equation in which y of 0 and y prime 0 is given to be 0 in our question. So after putting 0 to both these quantities, we get our simplified equation there. Now we simplify this equation as y of s because we need to find the time equations for y. We will simplify this to this, and by simplifying it more, we get this. Now, if we see this equation, we can clearly say that the y of t would contain would have, regardless of the values of a1, a2, a3, e to power minus 2t, e to power minus 2t, and e to power minus 4t as its time equation. That's what we needed to find in this equation. Apart from that, we can also find the values for a1, a2, a3. Now, to find these values, we can multiply s plus 2 for to find a1. We can multiply s plus 2 square on both sides of this equation and put s equals to minus 2, and then we can get a1. Using this technique, we can find a2 and a3 respectively also. So if you can see, we would find a1 equals to 3b by 2 by putting s equals to minus 2 and multiplying by s plus 2 square on both sides. Similarly, we can write a2 and a3. Similarly, for the second part of the question where we put u equals to ct, we would again use the Laplace properties on the both sides of this equation, and we get this equation. Regardless of what are the values of a1, a2, a3, we would get the t e power minus 2 and e to power minus 40 as our time equation for this problem. And similarly, we can find the values for a1, a2, a3, a4 by multiplying by s on both sides and putting s equals to 0, and similarly for s plus 2 and s plus. So, any doubt in this question? Any part we didn't understand?
So, Abhar, you can just hold on one solution, okay? One part.
Okay, gotcha.
This is A, okay, yeah. See, the key aspect here is that you have to bring in the notion of oftentimes the variables might not be separable. So in that context, you will have to bring in the notion of partial fractions. So that is the key aspect of it. You see that when you take the Laplace transform L, so it would become d square y would be ds square. So assuming that all y naught and all is constant for the time being, generally it would be given to you in a particular question whatsoever. So what are you eventually getting is, so you will have to isolate ys. So once you isolate is, what you would really see equation 1 contain multiple what you call non-decomposable terms which are not really useful for you when you use your Laplace table. So your Laplace table will have only standard functions. For instance, s plus 4, which is like s plus a. You may have s plus a square or less s plus a whole power n. You can find n to be 2. Okay. uh, so, Abar, could you just download maybe an online one Laplace table and show them? Yeah, textbook should be okay. Go to the table. So hold on here. So here what you would really see, these are the standard forms. You see that? This s plus a, s plus b, s plus b whole power and so on and so forth. But when you have your, when you isolate YFS, what you really see, they are not in the standard form. It is not there in the table, which essentially means that it's not very easy job. Then you probably have to apply the Laplace transform expression from first principles, which is like integral of e power st minus st dt, integrate from minus infinity to plus infinity, and it would not be most likely decomposable. So simplest way to do always when you are dealing with Laplace transformers, bring them into the standard form. The standard forms are all available in your table. So now we can go back. Yeah. See, 1 plus s square s plus 2 whole square times s plus 4 is not a standard form because you would not see a similar expression in the table. While a by s plus 2 square, which is like a1, so you'll have to calculate a1 whatsoever. 1 by s plus 2 whole square, 1 by s plus 2, 1 by s plus 4, they are all in the standard form. So you can use them directly from the table. Okay, so now what have you assumed here? The 3b by s plus 2 whole square now is decomposable as three components. Why there is a three component? So, I hope you again recall your partial fraction, which is most likely a plus 2, what you call 10 plus 2 math, or maybe at least you would have used in your MTL courses. So if there is a power, you probably need to, so s plus 1 by s plus 2 whole square, when you are making a partial fraction, you should make, so the various components that it would have is a by s plus 2 and a by s plus 2 square. The same thing over here. A by s plus 2 square, a by s plus 2, a in the sense a1 because both of them are different fractions, okay, and a3 for the third fraction. Okay, so now what have you done? You are decomposed them into the standard form. So you will be able to calculate the inverse of these terms, but not done. You need to know the variable values of a, B, and A1, A2, and A3. How do you do it? You will have to do some mathematical jigglery, multiply everything with, for instance, you will have to isolate somehow. So in this case, for instance, equation 2, to calculate S1, you have to multiply everything by S square. So what it would happen, A1 would be isolated, A2 into S plus 2, A3 times S2 square by S plus 4. So how do you get it? So now you can substitute S is equal to 0 or S is equal to minus 2 so that all the terms would cancel out. A1 and A2, you will be able to get, you will be able to isolate A1. Similarly, you do the same thing for other variables. So in the S plus 4 case, you will have to multiply the entire term by S plus 4 and substitute S is equal to minus 4. So you can just drag down. Let's move further. I think your screen is audible to you.
Yes, sir. Yes, sir. Audible.
Yeah, perfect. So that is all variables. And suppose you will be able to get it from the table by looking at the Laplace. So what are we interested to do? You need to get the so you wanted to get y of t, which means that what you need to really do, go to the next slide, next page. Okay, so eventually you are reaching, if you get all the three coefficients, you are done. So then it is perfectly fine for you. So the same applies for the problem 2 also, because see, whatever you are getting, eventually it should be, you should be able to calculate the inverse Laplace transform. Otherwise, what would be happening when you go to the Laplace space? You will be stuck. So when you really are writing as y of s, you should make sure that each of the components could be uh, you could be able to do the inverse. Uh, each of these components should be able, you should be able to perform the inverse so that you should be able to go back to the T space Laplace. So, so that's all about. Any questions? If you have, we can discuss that. That's the overall take home message that you need to know.
So can you please scroll down a little and read what was at the bottom? So B part, can you scroll down? All right, sir. Thank you.
If there's no question, we can move on to so in this question you can see two graphs. Just try to simplify these graphs in form of equation. There are many ways to solve these two types of questions. First is the standard way, and there are other ways also. So first, try to simplify this question into some form of equation, and then use the Laplace transform on those equations.
So this is more of a mathematical jugglery. So let's say you have different functions. Uh, so these are assumed that sometimes when you may have to deal with a little bit of input signal. So eventually every system you need to have inputs and outputs. So most often you would find out input signals of different type, and they would have to and you would have to deal with some of this. So this is like candidate examples. Okay, so we probably only look at 156. Let's only look at the pulse first one, and the second is of course you can go consider this as a homework. You see, these are again not in the standard form because you only know ramp function, you only know pulse function, you only know step function. So this is the thing that you would see in A is different than of B. So eventually, how do you can we decompose this non-standard function into standard form? Then again, what is our motivation? Apply the standard Laplace trigger. So how can we decompose functions into standard form so that you can use them? Again, you can use them in the Laplace domain. So otherwise, again, you don't find anything in your Laplace table and you would be stuck. And you cannot even write them. So how do you model the function in A? So it may not be possible. So this is like a summation of various small functions. So how to deal with such scenarios? So the take-home message is that if there is a non-standard function input or whatsoever, how do you write them as summation of various standard forms? So the two are candidate examples. There are many. You could see some of them in the textbook also. But the take-home message is that if you are given with such problem, how do you deal with it? Maybe we'll wait for a minute, 158 or so. Abar can explain A, and B could be considered as homework. And if you have some issues, we can take it. Okay.
Take a minute or so to try to solve the problem. Okay, let's start. So we can break this graph into three poles equation. First, when we are going from 5 to first we are going from 5 to 1, which is a difference of 4, and then when at time equals to 6, we are going from 1 to 0, which is the difference of 1. So we can write this equation as this. At t equals to 0, we have 5. At t equals to 2, we are down by 4, and at t equals to 6, we are down by 1. We can write this false equation as this. Then using
Bar,
the sorry, am I audible? Hello, hello.
so now it's better. Previously it was, yeah. Now it's better. Yes. Continue.
Okay, so
Please.
we can break down the following graph into pulses in three step functions. First, from 5 to going down from 1, which is the difference of 4, and then from 1 to 0, which is the difference of 1. And then we can use the real translation theorem. You can find the real translation theorem here, and you can use exact theorem on this part of the equation. By using this, you can get the following answer. You can directly apply the real translation theorem. Using the real translation theorem, the second part can also be done. You have to, I'm just giving a hint, you just have to decompose this following graphs into this type by using different slopes to get this graph. And by writing it on a mathematical form, you can apply the real translation theorem as we have done above and get the answer for the part B as well. Any doubt in this question?
So any questions? Yeah, so we are just overshot a minute, but we should wait for a minute. Again, you have to logically split it. So see, it starts with 5. So you see that at 2 it comes to 1. So what you have to do? You have to do a minus 4. And at 6 it goes to 0. So you have to again from 1 to 0 you have to do again minus 1. So for, at s of t, at like the starting, it is s of. So at when it moves to t minus 2 at the step, it become it does that step down, and when it becomes st minus 6, it do further step down. And so this now is a summation of 3 step function and with a delay. So step function with a delay, you see that. So step function with a delay. So step function. So when you take the inverse of a step, it would be 1 by s. Okay, so that is what taken out, and delay. So this t minus 2 would be e raised to minus whatever. So it is 2, it is 2s, 6, it is minus 6. So you might encounter similar problems when you deal with. So the take home message is that if you have like non-standard functions, how do you split them into standard form? So this is something that also you need to learn. So that's all for today, and I thank Abar, Aniket, Sarthak, and all the participants. And if you have some issues, we would resolve it in our doubt clearing session, which is on Friday. Okay, is that fine, all of you? You can just give a shout. Any questions? Ashutosh, Aranya, Divakar, Matulika. Am I audible to all of you?
Yes, sir, you're
Yes, sir.
Yes, yes, yes.
Okay then. See you guys. Bye bye.